All right. Thank you, everyone, for coming. I'm really happy to present Professor Juanita Boquel. She's just started at the University of Sherbrooke as of last October, and I'm particularly delighted because she is going to talk about one of the things I've been very interested in for the last 25 years of my life, which are defect centers in diamond. She's coming from the University of Basel, where I think some of this work was done under her postdoc. And she'll be telling us today about the low temperature photophysics that can be subjects in diamonds. Thank you.
I'm delighted to discover your physics department, what you're researching. Now I'll share a little bit about the work I've been doing recently. As you mentioned, the work I present today has been done during my postdoc before coming to Sherbrooke in the University of Basel. I'll talk about the temperature photophysics of NV centers, but also a little bit about nanoscale magnetic imaging with those same NV centers, and a few of my more, let's say, current research interests. Yeah. But let me start by moving into a little bit defects in semiconductors. In the name always sounds a bit so negative, defects in infinity, but actually this kind of system brings a lot of opportunities. As you might know, defects in semiconductors can be viewed in many ways as artificial atoms in such a way that they bring disparate energy levels. And among the defects that the most actually used are dopants, which are the base of the microelectronic industry, for example, like arsenic or phosphorus atoms and silicons. And those are usually electrically active. But there are also a different kind of defects, and those are color centers. Those are optically active. And this is the case of the nitrogen vacancy in diamond, which I will talk about today. In both of those cases, what's also interesting is not only they have different energy levels, but also some of those carry spins. And this is very interesting, whether it's an electron or nuclear spin, because this naturally introduces two-level system that you can then use as cumulates of boundary sensors. Another interesting aspect of those defects is that they are, by definition, atomic scale systems. So you can see here it's STM image or comparable images. Those are very nanoscale systems, and you can then integrate them into nanoelectronic or nanophotonics devices. This is a plus, especially because they are also good in the spin side of things to retain those long coherence times for possible system at low temperature and for the nitrogen vacancy at room temperature. So now I'll focus a bit more on the defect of the day, which is the nitrogen vacancy center in diamond. As the name says, it is made of a nitrogen atom next to a vacancy in the carbon lattice. And it has both an electron spin and a nuclear spin on the nitrogen atom, both of which have really long coherence times, even at room temperature. And that makes this particular system so special. The way those defects are made is most of the time using ideal implantation, followed by an annealing step. And in principle, the defects you should get are all identical. If you're wondering why we call this type of defect color center, it's because the way they absorb light actually leaves you with a slight color. Then you have a diamond with a really high density of those defects, which has this slightly pink or purplish color. But what is most interesting about those is the relation between their optical property and their spin property. So here you have the electronic structure at room temperature, and this becomes important later, of the NV center in diamonds. So you can see the ground state and the excited state are spin triplets. And when you excite, like most of the time, non-resonantly with the green light, you get photoluminescence in the red. If you look at the optical spectrum, it looks like this. You have the resonance emission at 675 nanometers, and the both sideband and photon sidebands also in the red. In fact, if you take a diamond with a lot of this defect and shine enough green light, you can actually see this photoluminescence quite high. This is actually quite impressive to see. What is most impressive, again, is the connection to the spin aspect. So if we now come back to this energy level diagram, we see that I have now added, besides the radiative path that is in the red, a non-radiative path that has more complicated structure than in the picture, but that is essentially non-radiative. And this, like, But this brings the system is involved. So in most cases, both spin states will have some direct variation in the red. They also both recombine through this alternative path. But what is different, depending on the system, is the rate at which it follows one or the other path. And for the first -1 state, this rate is actually about 8 times higher. And these bring about two things. So if you look at this graph, here you have the photoluminescence of the function of time as you start shining a green light on the system. So you can see is that at the very beginning, in the first half microsecond or so, you have a difference in light intensity depending whether you start in your spin 0 or your spin +1 state. It's a contrast of about 30%. This is what we call the spin contrast. What you also see here is that if you wait enough time, here typically over 1 microsecond, you will polarize your state into the zero state. You can see this from this level of photoluminescence to bright one. So in that way, we are able to optically initialize and read out the spin state of this system. But if you want to use it as a qubit or as a sensor, one more ingredient is needed, and this is the ability to manipulate the population from one spin state to the other. And with NV centers, this is done using microwave. This is what is shown here. So if you split the ground state using magnetic field to the zero interaction, you can spin the ±1. And when you sweep your microwave frequency and you hit this particular resonance and transition, your population transferred from 0 to -1, you will see the sharp decrease in photoluminescence that comes from the photophysics of the effect. And it's what particularly interesting is that the energy difference between those transitions is a direct measure of the external magnetic field projected on the NV axis. And this makes NV just excellent magnetometer in particular. It's a magnetometry that is also quantitative. If you want to use it as qubit or as quantum sensor, you can go a bit further and try to use those microwaves in whole sequences to be able to use it as a qubit. So you manipulate the spins on the blocks here. This is done using first calibration based on gravity oscillations, but then you can engineer all kinds of sequences that are typically coming from the NMR community to either make your center, your qubit, either more sensitive to environment or, on the contrary, decouple it from the environment, depending on if you want to compute or if you want to sense. Typically.
Tu peux parler un peu plus fort, en ligne, il y en a qui ont du mal à entendre.
Ouais, dans le micro.
Maybe
I should.
Sorry.
So that's the basics, if you wish, of the NV centers. And because of this versatility, also, there's a lot of work that has been done over the last 20 years, I'd say, or so. And I would say there's two main fields. One is quantum information processing, so using them as qubits. As been shown, you can use the electron spin, you can use the nuclear spin that's on the nitrogen atom, you can use the carbon spin on the carbon, the 13 carbons in the diamond, as well as spin and process observation as such. And that's been shown at low temperature, but also submersion at room temperature. The NV center, as I mentioned, is a natural spin photon interface. So this allows you to create networks. That's another avenue of research. And on the other side, you have quantum sensing. And here I'm highlighting only two of them that exist. One is to do nanoscale imaging using a single order sensor. And I'll say a bit more about this later. And another, which is impressive, and then here we also about mapping electric field, but at a completely different scale. So this is a product from the company is the Quantum in Sherbrooke. Million is working with. They're developing those very compact magnetometers based on these really large ensemble NV centers to get maximum sensitivity, and they are out to map the magnetic field of the Earth at scale, for example. So that's the introduction to NV center. Now I'll dive into the work that I've done in the last years. So first, I'll talk about the photophysics of the centers at low temperature and their spin contrast. So this body of work originated because I guess in the community, what has been seen is that, well, you can work with those energy centers at room temperature and low temperature, but there was a sort of a bit counterintuitive observation for sometimes that when those centers were cooling down, sometimes the optical and the spin properties would appear to be degraded, which is, usually when you have a quantum system, everything gets better as you go lower to temperature, but it wasn't quite the case. And this was observed by many groups, and since things work relatively well, I think there was not really a second thought given to this aspect. So you can see here, photoluminescence drops below 50 Kelvin. Here you see both photoluminescence decreases and the ODMR contrast that I showed on the magnetic resonance is also clearly suppressed, and this also happened to depend on magnetic field in this case. So what we did in Basel is an experiment that had not quite been done, I think, probably from technical reasons. So we cooled down those centers in a cryostat that has a strong magnet, in which we can apply the field along the MB axis, which, mind you, is not but about 54 degrees shifted. And this is something you can only do if you have a vector magnet for those very high magnetic field. And I think that's the reason why people didn't look at this that way. But anyway, if you do that and you sweep your magnetic field, that you will see that the photoluminescence level that you have drops at certain value of magnetic fields. Here you have the full photoluminescence, typically the same as you have at room temperature. But you have those deep state magnetic field value where you have drop in photoluminescence. And to understand this, you need to look at the energy level structure of the same effect, but this time at low temperature. You will see here, as you can see, it's a bit more complex than what I showed earlier. The excited states exactly now in orbital doublet, each means to the LC triplet. So yeah, the physics resembles, but there is this added complexity that there are 2 orbitals and 6 excited states. And if you look at the evolution of these states under applying fish, which correspond to what we did in the experiment, you see this evolution. And in particular, I want to bring your attention to those particular bonds here where you have avoided crossings. Because if you then look at the experiment, you can see that these decreases in photoluminescence appear exactly where you have this avoided crossing. And this we can understand very well. And in fact, it's something that is also observed at room temperature at its spin value. This corresponds to anti-crossing at those states. You don't have your pure states, you have spin mixing, and this will, through the mechanism I've shown earlier, will decrease both the photoluminescence but also the spin contrast. So if you think about using those NV centers in this particular region, what you will see is you have a really strong reduction in spin ionization, in without any overall sensitivity to external fields. Actually, for sensitivity is sort of a double penalty because you lose both contrast and full number of counts that you are extracting from the system. And then we decided to tune the system a bit differently. We decided to try to reconcile this low temperature picture that we now understand better to the room temperature version. And this is what is shown from this plot. So what we've done is those magnitudes in soup as a function of temperature from 4 Kelvin to 300 Kelvin, about 30 Kelvin or so. And what we see is the following evolution. What you see at the beginning is that those level anti-crossing, they will broaden. And in fact, around 50 Kelvin, you have this really strong broadening that, in fact, most for the magnetic field that we have available in our cryostat, which maybe is also a Tesla, you have a really strong reduction across the range. And finally, here you have sort of a recovery of the photoluminescence. And then finally, you find yourself about 150 Kelvin or so in the room temperature picture. And this we understood relatively well, what's right behind it. And we also developed a quantitative model based on the full low temperature Hamiltonian for this particular defect, taking into account parameters that we extracted from experiments at low temperatures. We also included rates that are temperature dependent, everything that has to do with phonon. And we used mainly modeling this rate, but also more importantly, this rate, which is phonon relaxation related rates that basically meet the two orbitals. So you have this very increasingly fast spin conserving transition that occurs between the orbitals. And those increases as the temperature goes up. And then effectively, and I've not shown it here, but effectively at room temperature, you get a single orbital, so you get an average of those two. And when you have a single orbital, then you find yourself with a single acyclic state anticox.
Sorry, what kind of phonons are the main ones in the mixing case?
Things like acoustic phonon, and it's a two phonon driven process. It has this 3 to the 5 scaling with temperature. Yes. Yeah. Great. So, yeah, so this process is driven by orbital averaging, a little bit in the same way as we have motional averaging, I think, with some molecules, for example. So, but okay, this was done, as you can see, through the experiment I've shown. Like this was done on a single energy centers, but if you start looking at different energy centers, they are, of course, and unfortunately not equal. And one in difference from when you change the center from one center to the other is actually the effect of strain. And this we also investigated as systematically as we could. We looked at energy centers that are in the bulk, so we still have a photonic structure with solid conversion rates to extract more light, but the ND centers is micrometers away from the surface, versus ND centers that are about 10 nanometers away from the surface in a nanoscale. And when we do this, we see those magnetic field sweeps in photoluminescence that we get from these are quite different. You see the position of those peaks are changing. And that, in fact, is not so surprising, because if you change the energy levels that are so discrete, they change with almost any external field, including strain. You can see the corresponding energy level diagram. You can see where the crossings are occurring. And with a radiograph model, you can then, with theory, just sweep the entire strain values. And we see that this energy center has a low strain, we find it somewhere here, and this is a high strain. We actually asked of this plot. Right. So, yeah.
Are you applying the strain?
So in that case, we are not actively applying. We are looking at an energy center that is far below the surface, and it's interestingly low strain compared to an energy center that is about 10 nanometers from the surface in a nanofabricated dynamic structure. Yes, this is a theory, but this we are not able to do experimentally. And that's in a way too bad, because actually for the experiment, you want to be out of those regions where you have degraded spin contrast. And you can see that one solution is to apply magnetic fields, but again, this is not always available for all experiments in all parasites. And the other is to have extremely low strain at one of those regions, but again, as soon as you go in nanofabricated structure, you typically always find yourself in that regime where at low magnetic field you have degraded spin contrast through mixing. But with in diamond for the NV centers, there's another degree of freedom that couples in a way that is a bit. I'll skip this. That is coupling to the NV center in a similar manner. That is electric fields. So while we cannot change and tune the strain, we decided to try and tune the electric field and see if we can, what we see in that case. Electric fields are usually used for color centers to try and tune the energy levels so that is not novel. What is novel is to look at those excited anti-crossing features that I showed earlier as a function of applied gate voltage. So here you see a 3D map because structure. Because I've got these versus all gates, but you can recognize the shape of the diagram that I showed for the structure. So you can see that we have a very long tuning range. If I now show the map, we can see that we reproduce the plot we had obtained for in the theory where we changed the effective strain that the ND center experiences. So in a way, with the electric field, you can, to some extent, put yourself in one of those regions. I think, but when applying large electric fields, other problem would arise for some of the applications that I mentioned earlier. What we found more interesting, actually, is that those features are very similar to the magnetic resonance transition that I introduced at the beginning. And in particular, that those ones are very sensitive to electric field, and in a way that might actually open a path towards electrometries, which is something that is not really common with NV centers, which it's mostly about magnetometry. It's also possible with those features, but in the end, one is not really gaining any sensitivity compared to just looking at the stark shift from the ground state. So I'm not showing this today, but in most of these days, they're trying to, and this first proof of concept of this, of electric field detection and imaging based on those features and not on the magnetic resonances. So with this, I come to the end of this first section that was about photophysics. Just to say a few words. So yes, we investigated the photophysics of NV centers under large parameter space, from temperature to not shown here, and strain. And this allowed us then to develop a new sensing method. This is what you get when you look more carefully at the visibility effect, but also find possibly mitigation strategy when it comes to using them as low temperatures. And now I'll switch to something very different and much more technical and applied, which is magnetic field imaging with those NV centers at low temperature, and especially our efforts to make this happen below 1 Kelvin. So let me introduce you first the technique, scanning NV microscopy. It's based on a scanning probe approach. You have an AFM assembly, and the difference is that we have not silicon tip, but the all diamond tip with a single of those NV centers about 10 nanometers from the apex. In a scanning probe setting, you're able to scan above a sample of interest, while at the same time record the response of the NV centers to the local magnetic field. And this creates an image of straight fields that you can then on which we can calculate the magnetization, for example, of circuits. It is not a very good AFM in itself. It has only about 40 nanometer spatial resolution, and the magnetic field sensitivity for DC is about microtesla per unit. As I mentioned earlier, magnetometry with NV center is quantitative. It works at room temperature, it works at low temperature, though the contrast might be slightly less. And it is also importantly non-invasive approach. So here I'm just showing work of some colleagues in Belgium that just as an example that what is being done these days with this technique, a lot of it is done on 2D magnets. So here is this antichromatic 2D material from sodium bromide. They have prepared a sample with different layer thickness, bilayer, trilayer, 7 layer. And this first image, so that's an ideal magnetic field image. The first image, their system, the initial magnetization, magnetic image of the system. You can see different magnetization depending on which layer you are, and different they correspond to the magnetic orders. And what they've done between those two images is that they apply a strong magnetic field. And with this, you can see here from the different color, they're able to switch the magnetization in this five-layer. But the precision is such that they can also see that this flip is inducing a change in the bilayer next to it. And in fact, you can also see, can also resolve the magnetic dominant wall that is induced as a consequence of this change here. And not only they are able to see that there is a dominant wall that is initiated, but they are not showing this here, but this is something that they could then study, like they could see the propagation of this dominant wall, magnetic dominant wall in the sample. And mind you, the domain wall is something that is a nanoscale, that is also a nanoscale feature. That was just to illustrate what has been done with scanning NV magnetometry at low temperature. And maybe just put this a little bit in context rapidly. I think the main techniques that are in the same field are magnetic force microscopy and scanning screen microscopy. I think the trade-offs are typically the spatial resolution of each technique and the sensitivity to magnetic field. And scanning NV magnetometry has like it's somewhere lies in the middle. Like the spatial resolution is better than the discrete version, but the sensitivity is less. The MFM is doing better in some other ways, but it has magnetic tips, so you actually can influence your sample. So which technique you might want to use depends on the study you want to carry out. As a result, and I'm just looking at it quickly, but like a lot of different condensed matter investigations have been carried out at a macro scale using this technique. So I highlighted magnetism, but you can also image current that produces magnetic field. You can look at vortices and superconductors, and you can also do noise spectroscopy, and all these spatially resolved. And this is why it would be very interesting to be able to have this technique working at millikelvin temperature, because you have a lot of those non-bonding material with very exotic phases that are only visible in this regime of temperatures. This is what we set to do. And so, as I mentioned, a lot of it is done with optics. We are sending light. But when it comes to working at millikelvin, the light is not the problem. The problem is the fact that we need microwaves to manipulate the stimulus. And it is quite difficult to bring about all those measurements that are scanning probe measurements, and I'll explain one in a second. So, as I mentioned, it's an AFN based technique, and we use a tuning fork for force detection. It is shown here. You have a glass capillary that is glued to the tuning fork, and you have this diamond scanning probe that is glued to the capillary. The question is, where is the microwave delivery coming from? There's different approach. You have externally mounted wire that are rolled as close as possible to the scanning probe. You have bond wires across the sample. We bring the particles in proximity, or you have on-chip strip lines for it. But what we really would want was actually the following list. You would want that the distance between your NV center, your sensor, and this microwave delivery solution stays identical at all times. Especially if you're doing pulse measurement, pulse microwave, you want that the power delivered at the center stays the same during your measurement, that is, while you are moving your tip, so while you're scanning. Finally, at low temperature, none of the solutions provide a large scan area. Same, since the distance between the microwave lines and the NV center is relatively large, you need to apply a lot more power. This way becomes problematic for millikelvin operation. And also just the ease of use. Any user would want something you don't spend 2 days trying to align just to before starting your experiment. In the recent years, so none of this is ticked by any of those approaches. In the recent years, there have been some efforts. So you see handcrafted bond wire put in place with tweezers close to the scanning probe. Same with integrated wire group, the devices done one by one. And more recently, some actually by a company that's setting this type of magnetometer, a side antenna that is has the merit of having this possibly simple and reversible manufacturing, but that is also relatively microscopic and quite far from the NV centers. And I said this is problematic if you want to minimize your the power you are using to drive your NV center space. So we developed a solution for this, or the beginning of a solution, by integrating the microwave line with the support structure for the line probe. You can see here you have the tuning fork for the AFN, and then we have this really long, really relatively microscopic monolithic structure that is made of fused silica, and that is put into shape using this laser-enhanced etching by a company called Femtoprint. So that's what they do. And the only thing we are doing then in the lab is to evaporate gold onto the structure, and it's made in such a way that your connecting line is then ready to use. Yes, at the front here you have a loop in which you can have optical access to the end centers. And what I want to stress here is that this line that delivers microwaves comes to about 15 micrometers from your sensor, and it is not changing over time since it's integrated into your raster scanner. So here you have a view of the structure and the sample we looked at to test the performance of this probe. This is a cobalt and boron ferromantic alloy. And what we see when we first check is the AFM performance of these probes, and we can see it's very equivalent to the capillary version. And this was not a given because we are putting on the tuning fork something that is quite heavy, and that could just also influence the modes of this tuning fork. And actually, it's much easier to mount the probe in this way. That was the second time. We are much faster at doing it. And for the sensitivity, well, this does not really depend on the structure. This is mostly defined by the quality of the NV center or of this response, of the spin property of the center. But this is not what we're looking for. What we're looking for is the spin manipulation and the microwave power. Here I just show like the simplest experiment that we run with centers. So here we have again the completed electromagnetic resonance as a function of microwave power. Same here for our station. Then, in fact, we are able in this geometry to derive our spins very fast. We have very strong power, but we have radiofrequency up to 25 megahertz. And I must say that I think for experiment, typically one does not need more than 5 megahertz of radio oscillation. So well within those limits. But again, this is not the figure of merit that we are looking for. What we want to know is how much does the experiment heat up when we do this. And these turn out to be quite difficult to quantify. So this is my best attempt at bringing the different measurements together. In the shaded area, you have the same range of microwave power. It's about 100 milliwatt entering the cryostat. And we do not know how much is dissipated at the probe. And then we can read out different metrics. First of all is the sample temperature as read on our sensor, which is the first thing we looked at. And you can see, so we were operating at 4 Kelvin. And you can see that even from this sort of 100 microwatts entering the cryostat, the temperature on the sensor would only show an increase of about 150 millikelvin. So we're quite excited about this. Until we decided to continue applying stronger power. And then what we start seeing is that the photoluminescence of our NV centers started dropping. And this we know from our photoluminescence studies, the photophysics that I presented earlier. This means we are warming up the NV center. As I showed earlier, as you increase the temperature, you first have this decrease in photoluminescence that we rise at 100 Kelvin. But we started then with the microwave power entering those machines. So this is shown here. Now here, and then we are able, just by applying microwave to this step, go all the way to what would correspond about 70 Kelvin locally at the NV center. So what is the temperature of the experiment, of your sample when you're looking at it? Not somewhere in between. This is something we cannot really pinpoint at this stage. I guess we have results found, but it's not really helpful. And experiments we have not done, but should be doing, is a bit different than that one. So here we apply the microwave continuously, and we know that that's not good, and this is also not how we plan to do experiment at millikelvin temperature. Then we will rely on pulsed microwave sequences. And if we extrapolate from these changes in temperature, based on what we see in continuous mode, based on the duty cycle of the sequences we are planning to use, there, in this slide, it's difficult to see here, you can see that probably in this geometry we are dissipating a lot less heat than the current geometries. where we have them correct respond. But really, what we need to do is to further cool down those NV centers and those structures, and this is planned. It's not been done. Yeah. So this is what the story is at the moment for millicandic operation of scanning NV manufacturing in Basel. And now I'll just say briefly a few words about a few projects that I want to start in Sherbrooke. And for this, I'll first something very broad. So the direction of interest, the two of them are really close to what I just shown. Is this engineering and study the properties of color centers in particular in nanoscale devices. Know that this brings about some opportunities, but also some difficulties. So that includes doing nanofabrication and optical electrical spectroscopy. And one aspect of this is to take the methods that I've shown here and try to apply that to other color centers than NV center. Another, through collaboration, is to continue with scanning probe experiment, which I've worked on for many years, well before doing NV center research. And then I want just to spend a few more minutes talking about the last two, which is charge state control for transduction and sensing opportunities. Just so that I need to mention something I haven't so far, is that all these I'm mentioning NV centers, but in fact, I'm only talking about the NV center that is in negatively charged state, NV minus. This is the object I've looked at. But there's a different charge state in which each of the disks spend time with being stored. And this is the neutral charge state. So when it loses this electron, and you can already tell that if it loses the electron, this is a bad sign for anything that has to relies on the spin of this centers. Yeah, so that's technical image of the spectrum of the NV0. So there are two different charge state of the sense issue. And any NV center spends time in one and the other. For NV center research, in general, we try to optimize the time in which is spent in the useful state, which is the NV minus. And this is the studying NV minus, which I want to work on. What I want to work on also is to stabilize the NV0 state. I'll explain why. And also being able to switch from one to the other in a dead instant manner. So let me see if you work about why NV minus. I think this should be relatively clear from what I presented today. But if you spend more time in the NV center, this is where you have the electron spin that is your sensor or the qubit. And then the more time you spend in this, maybe I haven't really fully mentioned another aspect. In diamond, it's really difficult to extract photons. So anything that I've shown so far, like readout, is not single shot. We are averaging this over thousands of times, right? But when you do this, you are losing to like bad initialization, for example. And one type of bad initialization would be if you're trying that you're doing a useful sequence, but your NV is not in the minus state, but your NV state. So your sensitivity, anything related to that, will depend strongly on the control you have over the stability of this NV minus state. And there's a lot of strategies that are being developed. It involves a lot getting control over the surface, co-doping, so changing film levels in environment, or acting on the optics to either induce or prevent a certain type of ionization. So a few questions I would like to explore, or topics I would like to dive in, are related to this. So especially the effect of electron confinement in that in this respect. And with this comes the study of child dynamics at the diode scale for those specific defects. And this is all in the hope of being able to enhance the sensitivity and the efficiency, if you wish, of all the current applications based on NV minus on the NV centers. And the second as I mentioned, is to stabilize NV0, the charge state that so far nobody really wants to stabilize and try to avoid. And in its neutral charge state, it becomes something quite different, and in a way, it becomes closer to the excited states that I've shown earlier. So it is more sensitive, this level structure that's shown here, because you have all the ground states splitting. It's more sensitive to electric field. This has been shown by this group recently, but it's also more sensitive to strain, as expected, but not quite shown. Well, this keyword. But the temperature sensitivity in the midi-Kelvin range is of interest. And finally, it actually carries a spin, though maybe not as robust as the one from NV minus. So this is also a question to answer. But what I'm more interesting is to study the fundamental physics between the interplay between spin and orbital physics for the system and about temperatures. Especially again, we'll try to dive into the dynamics of those of these processes to try and also extract the sensitivity of these two external fields. And all this is to adhere to our sensing and or transduction depending on which degrees of freedom we are investigating. That's for B0 in short. And then lastly, it's about being able to deterministically change from one to the other. Why would we want to do that, except for stabilization? It's because it is possible, for example, to change the readout from the conventional one that I mentioned earlier to increase the flexibility or to enhance it by mapping the spin state into the charge state. And what you gain with this is the photoluminescence from the NV0 versus NV minus is stronger than the spin contrast that you get the way I described it earlier. And by applying a certain window of time, like by timing or experimenting in such a way, you are able to take advantage of this difference and have a readout that is more robust. Okay, but that exists, and so that wouldn't be new. But when it comes to being able to do this deterministically, because if you rely on the charge state to read out your spin, once you change your charge state, you need to go back to your initial charge state, so you can again map the spin into it, etc. But especially this path of converting it back to the NV minus is something that is not always straightforward, at least not with simple equipment or expensive equipment. And for this, I think there's a lot to study about ionization dynamics, especially as a function of temperature. I think this sort of readout is highly temperature dependent in its efficiency. And there's also a lot of unexplored questions, and we stumbled also on those things at low temperature when doing the photophysics work, where we could see that there's additional prices in which you can ionize this system. So, and once you gain more control over this, you can then build control sequences where you take advantage of the charge, but also, for example, the nuclear spin into your readout. And again, this will bring about like a specific type of readout options of sensing modality that I'm hoping at least that it will improve a certain type of experiment, which is the ability to measure on multiple of the single color centers at the same times. And this brings me to the end of this talk. I'd like to acknowledge the team in Basel, which my work in the last few years. So start acknowledging the people in Sherbrooke that are helping me start this lab. So you mentioned that there's positions, and I will also thank you for your attention today.